Hello everyone. In the first lecture, we discussed about the historical aspects of the phenomena of radioactivity, and also how the different types of radioisotopes are there, whether they are occurring naturally or they are produced artificially, and how they find these applications in different areas. Today we will go into the fundamentals of radioactive decay, and as usual I will just briefly mention that at the end of this lecture you should be able to answer these questions. For example, what is radioactive decay law? What is half-life and how to measure it from the experimental data? What is mean life of a radioisotope? What are the units of radioactivity? How does the activity of a daughter nuclide depend upon that of the parent activity? And how does the radioactive decay in the case of branching? So we'll discuss these details in the details of this lecture. Okay, so let us discuss first the radioactive decay law. We have just taken an example of a radioisotope A, which is undergoing some decay. It could be alpha or beta or gamma to B. So the A is called the parent and B is called the daughter. So henceforth, when we say parent, means it is the parent isotope which is decaying, and whatever is formed we call it daughter. Now the radioactive decay law is like chemical kinetics in chemistry. In chemistry you have the order of a reaction, like if A going to B you may say it is a first order reaction. Radioactive decay also follows the first order rate law. In the first order rate law, the rate of decay, that is if n is the number of atoms of the reactant at any point of time, then minus dN by dt is the rate of decay of the atoms per unit time, is proportional to the number of atoms at that point of time. And if you remove the proportionality constant, this lambda becomes the proportionality constant. So the rate equation for radioactive decay becomes minus dN by dt equal to lambda n. So this is a first order rate equation, and if you want to find a solution of this equation, you integrate this equation. So if it is an indefinite integral, so minus dn, you arrange the variables, a minus dn by n equal to n integration dt plus a integration constant c. So now you can put the limits here. That is, the solution of this will become ln n equal to lambda t plus c. So now how do you find the c? When t equal to 0, n equal to n0. So you put this condition minus ln n0 equal to c, because t is 0. So you get minus ln n equal to lambda t plus ln c ln n0. Rather it will be minus ln n0. So it will become minus ln n upon n0 equal to lambda t, or you can say n upon n0 equal to e raised to minus lambda t. This is what is the expression for the decay of a radioisotope. So n is the number of atoms decaying with time, and the number of atoms decay exponentially with time. N0 is the initial number of atoms. So the exponential decay of radioactivity is the signature of first order rate law that governs the radioactive decay law. So this I have shown here as a function of time. If you plot the number of atoms, then activity follows exponential decay. Now from this graph, you can, if you want to find out the term called half-life. So what is half-life? Half-life is the time when the number of atoms have become half. So suppose initially there were N0 atoms, the time when the atoms left are N0 by 2, we will call it the half-life. So you can just draw on this graph, find out the time when the active number of atoms have become half. So from the exponential data, it may be difficult graphically to find out the half-life, but we will discuss very soon how to make it more accurate. So when n equal to n0 by 2, t equal to t half, and so you can substitute the value of t in this equation and find out what is the value of t half. So t half will become ln2 by lambda. How do you do that? You can see here, that is n upon n0 equal to e raised to minus lambda t. To take the logarithm, ln n by n0 equal to minus lambda t, and so lambda, so it becomes, so when n by n0 is 1 by 2, lambda t equal to ln n0 by 2, n0 by n, and n is nothing but n0 by 2, so it becomes ln 2, and lambda t becomes t half. So you can see here, lambda becomes equal to ln2 by t half, or t half equal to ln2 by lambda, and so it is ln2 is natural log of 2 is 0.693 upon lambda. So this is the relationship between half-life and decay constant. So if you find out the half-life from graphically from this exponential decay, you can find out the lambda, or later on I will show you that if you find the lambda, then you can find out t half from another type of plot which I have shown this one. Now most of the time we don't determine the number of atoms. What we determine is the activity. So the activity is nothing but the number of atoms decaying per unit time. So minus dn by dt is nothing but activity, atoms decaying per second, and it is given by n lambda that you see from here. So activity is nothing but number of atoms into lambda. So activity becomes equal to a0 e raised to minus lambda t. So you can, if you plot activity functions as a function of time, this also will follow the exponential decay because lambda is a constant. So before we proceed further, since when we do measurements, we don't measure the activity directly. We measure the counts. Our detector system gives you counts, and so if you say counts per second, we have to convert into activity. There are some factors called detection efficiency and so on. So the units of activity, like activity we'll call as minus dn by dt, number of atoms decaying per second, equal to n lambda. So this is called disintegrations per second. And to honor the discoverer of the phenomenon of radioactivity, we have a unit of 1 becquerel is equal to 1 disintegration per second. Also, there is another unit of radioactivity called Curie, in the name of Madame Curie, and 1 Curie is 3.7 10 power 10 becquerels. So you can see the Curie is a much bigger unit compared to becquerel. So how does this number come about? This 3.7 10 power 10 becquerel actually is the activity due to 1 gram of 226 radium. Radium was discovered by Madame Curie, and therefore the activity of 1 gram of 226 radium has been defined as 1 Curie. Now you can find out in terms of becquerels what will be equal to 1 Curie. The half-life for 226 radium is 1600 years. So you put in the equation activity equal to n lambda, number of atoms in 1 gram of 226 radium will be Avogadro number 6.023 10 power 23 atoms in 226 gram. This is the n in 1 gram into 0.693 upon t half, that is lambda. So 1600 years into 365 days per year into 24 hours per day into 3600 seconds per hour. So the units get cancelled, and so you have seconds. So you have atoms per second. And so if you do the calculation, it will come to 3.7 10 power 10 atoms per second or becquerels. So the Curie is a very, very large unit. You can see that 1 gram of 226 radium is very difficult to handle. So normally we don't handle Curie level of activity. We handle, in fact, even less than microcurie level of activity. So there are other units called millicurie, 10 power minus 3 Curie, 3.7 10 power 7 becquerels, microcurie, 10 power minus 6 Curie, 3.7 10 power 4 becquerels. Sometimes even we can have even nanocurie also. So for activity handling in the laboratory, people use becquerels, 1 becquerel, 10 becquerel. But if you are using for industrial applications like a radiation source or irradiation, you may be handling hundreds of curies. Now let us go a little further. I was mentioning about determining the half-life from the decay data using the activity. So activity is A0 e raised to minus lambda t, where A0 is the initial activity. So just a little bit of manipulation. If you see, if I take the logarithm on both sides, then ln A is ln A0 minus lambda t, and now see this becomes a straight line of ln A versus t. So you see here what I have plotted here is ln A on the y-axis and time on the x-axis, and it becomes a straight line. So it will become easy to understand and handle also. So the slope of this line is lambda, and from the activity data also we can now find out the half-life using a paper which I will call as semi-log paper, because on the y-axis I have the logarithmic unit, on the x-axis we have the linear unit. And so when we plot activity, actually we will be plotting the count rate. So the activity of radioisotope is disintegration per second, but when we have the experimental data, we will have the count rate in detector, and the count rate can be counts per unit time, it could be counts per second, it could be counts per minute, and so on. So that I will discuss now in more detail, and it will be very interesting if you understand to follow this semi-log paper. What I have shown here is a semi-logarithmic paper. On the x-axis we have the time, let us say it is hours, so 1, 2, 3, 4 hours. So this is larger graduations. You can see there are the bold lines on the x-axis. You will find vertical parallel to y-axis, they are 1, 2, 3. This is in time in linear scale, and on the y-axis you see say the scale already made in logarithmic units. So it is cycles. You have 10 here, 100 here, 1000 here. So it's called 3 cycle paper. You can plot the data on 3 orders of magnitude: 10 to 100, 100 to 1000, 1000 to 10,000, and so on. So now when you plot the counts on this scale, you don't have to convert the counts into log, because the scale is adjusted like that. So you see here, when I say 100, next point is 200, 300, 400, so on. When you have 1000 here, then you have 2000, 3000, and so on. So if you understand how to use a semi-log paper, activity data handling is very, very simple. So what I have plotted here, the decay of a radioisotope on a semi-log paper, and as I discussed in the previous slide also, even here also you can see the logarithm of the counts versus time will be a straight line. Now instead of ln natural log, you plot here the log base to the power 10, And so logarithmic plot of activity will have a straight line behavior. And now from here, suppose the initial counts was 1000. When counts become 500, so this is 500 at this time. And you can read on the x-axis the time is 2 hours. So straight away from the semilog paper, you can find out the half-life in a much simpler way. Once you find out the half-life, you can find out the decay constant lambda equal to 0.693 upon T. Now there is another quantity called mean life. So what is mean life? Mean life is the average time a radionuclide survives. Half-life is when half the atoms have decayed or half the atoms have survived. So from the radioactive decay law, n equal to n0 this one lambda t, let us find out how many atoms survive or what is the time required for the survival of radionuclide on the average. So if you have a function and you want to find out the average, how do you find out? So you want to find out the mean value of t. So you can take the t dn, integrate over 0 to n0 divided by the total number of atoms, that is integration of dn over 0 to n0. So now you can write here now dn equal to the derivative of n here. So dn will be n0 lambda e raised to minus lambda t upon n0. So you can see now the variable has changed from n to t, and so the limits of will become 0 to infinity instead of 0 to n0, because the radioactive decay, that exponential decay, now the curve will meet the x-axis at infinite time, and therefore the time can go from 0 to infinity. Upon the integral of this will become n0. So what you have here is now n0 will cancel. So you will have lambda t e raised to minus lambda t dt, and if you solve this integral, you will find it will become 1 by lambda. You can do it at your home and find out whether it becomes equal to 1 by lambda. Now there is one more way of deriving the expression n equal to n0 e by lambda t based on statistics. In statistics, we say lambda, the decay constant, is the probability of decay of an atom in unit time. So if that is the definition of lambda, then what is the probability of survival in unit time? 1 minus lambda. Lambda is the probability of decay. The probability of survival is 1 minus lambda. You have a unit time interval delta t, let us say. In delta t, what is the probability of survival of an atom? It will be 1 minus lambda delta t. And now you want to find out what is the probability of survival till time t. Then this time t we can define in terms of n delta t. That means you divide this time interval into a large number of delta t intervals, n intervals. So it becomes 1 minus lambda delta t to the power n. You just multiply the probabilities over the n intervals. And now when delta t becomes very small or n becomes very large, so n tending to infinity, 1 minus e raised to minus lambda t upon n to the power n. So this is actually, you will see, limit n tends to infinity, 1 minus e raised to minus lambda t upon n to the power n will tend to, no, it is not e raised to 1 minus lambda t upon n, it will become e raised to minus lambda t. And so what you have here is the probability of survival till time t becomes e raised to minus lambda t when n becomes very large. So the fraction, if there are n0 atoms in the beginning, What is the fraction of atoms that survive till time t? N by N0 equal to e raised to minus lambda t. So you have N equal to N0 e raised to minus lambda t. So that is how, from the fundamental definition of lambda as a probability of decay of an atom per unit time also, you can derive the expression for radioactive decay. Okay, now there will be many situations when you will encounter two independently decaying radioisotopes. So you have A1 and A2 are two isotopes decaying independently. They are independent of each other. So A1 is decaying with its own half-life, A2 decaying with its own half-life, but it's a mixture of activity. So when you plot such an activity on a simulog paper, so when I am saying LNA, essentially I am plotting on a simulog paper. So you see here, the total activity will be the red line. Now, so how to resolve such a data? On a simulog paper, when the half-life of the two isotopes are different, so at a much later time, when the short-lived isotope has decayed, you can extrapolate the linear portion to 0 time, and what you get is the activity of the short-lived isotope, a long-lived isotope. And when you subtract this activity of the long-lived isotope from the total activity, you get this data. That is the pure activity of short-lived isotope. So extrapolation to 0 time gives you initial activity of the two isotopes, and from the slope of these two you can find out their half-lives. So you can, using simulog papers, you can resolve the mixture of two activities into individual isotopes' half-lives and their initial activities. There is another case of branching decay. That means the same radioisotope decays by two modes. So A going to B and C with different decay constants, lambda 1 and lambda 2. Now, in such a case, so the decay of the parent, you can say minus dNA by dt equal to Na lambda A, which is nothing but the growth of A, B and C separately. Now this you can write dNB by dt as lambda 1A and this is lambda 2A. So the decay to B and C can be written as now lambda 1A. These are two branches of decay of A. So this is lambda 1A is first part, lambda 2A is second part. You take Na as separate, become lambda 1 plus lambda 2 into Na. So this becomes the decay constant for the radioisotope A is the sum of the decay constant for the two branches. It is like, if you have a tank and it has got two outlets to empty it, and you open both the taps, then the tank will empty, and depending upon the diameter of the two taps, the flow will be different. The time taken to empty will be different. So it is similar to that. So this equation lambda equal to lambda 1 plus lambda 2, you can replace lambda 1 by t half. 0.693 upon t half is for the parent equal to 0.693 upon t half 1 for the lambda 1 and 0.693 upon t half 2 for lambda 2. So you can cancel the 0.693, that is the ln2. So 1 by t is 1 by t1 plus 1 by t2, or t is equal to the half-life of the parent equal to t1 to t upon t1 plus t2. That is t1 t2 are called the partial half-lives for decay into B and C. So the relationship between the partial half-lives for the two branches to the parent half-life is the way. So but when you measure the activity of either B or C, the half-life that you will get that of the parent, because if you measure the rate using one tap in a tank or another tank, the tank is getting empty anyway. It is decaying by both the taps. So the half-life that you will get while measuring either B or C will be the average half-life of the radioisotope. So this is a important, like I will give you an example where this is the isotope copper 64. The copper 64, if you recall, I will tell you later on in terms of the masses, it can decay by both beta plus as well as beta minus. So in beta plus decay it becomes nickel 64 and beta minus decay becomes zinc 64. Now the average half-life, so when you do the measurement of half-life of copper 64, you get 12.7 hours. But when you calculate the partial half-life, so you calculate partial half-life of this copper 64 for beta plus decay or beta minus decay. I am writing here beta plus comma electron capture, that we will discuss in radioactive decay, nuclear decay data. But right now we will assume that this is the one channel. Beta plus EC is one channel. So this is called electron capture. When beta plus decay does not happen, then there is a competing mode of decay to beta plus decay, that is called electron capture. We will discuss this more details in the nuclear decay. So now decay constant for copper 64 is 0.693 upon T half, and that T half is 12.7 hours. So you can write is equal to 0.0564 hour inverse. Now how do we get the partial half-lives for decay into nickel 64 and zinc 64? We set up two equations. Lambda 1 plus lambda 2 is equal to 0.0546, that is the lambda, and lambda 1 by lambda 2. So here the branching intensities are given. 61% of the time nickel 64 is formed, 39% of the time zinc 64 is formed. So I can write lambda 1 upon lambda 2 is 0.61 upon 0.39, that is 1.564. So I have two equations, lambda 1 plus lambda 2 equal to 0.0546, lambda 1 by lambda 2 0.61 by 1.564. So I can solve these two equations to find out lambda 1 and lambda 2. So lambda 2 is equal to 0.0213 hour inverse, lambda 1 equal to 0.0333 hour inverse. And now we can convert this lambda into half-life. They are called as the partial half-lives. You see here, the partial half-life for decay to nickel 64 is 20.8 hours. The partial half-life for decay to zinc 64 is 32 hours. And the average half-life is 12 hours. So you just see here, the partial half-lives are more than the average half-life because it is decaying by both routes. So it is less than both the half-lives. So what we discussed today was the radioactive decay and different types of decays, like the decay of a mixture of radioisotopes or the branching decay of a radioisotope into different modes like beta plus, beta minus and so on. And so in the next lecture I will discuss the radioactive decay chain and the growth and decay of the daughter products. So I'll stop here. Thank you very much.